So we're getting to the end of this is lecture 6. Next week is GPUs and GPU programming, and lecture 8, which would be data parallel programming and data parallel thinking. And then there'll be a bit of a switch in the class. So I do a bunch of software and performance optimization lectures for the first 8 lectures. Then Kunle is going to come in and tell you a little bit about hardware and things like that. So that's where we're going. Okay, so if on Tuesday was about scheduling. So we talked about different strategies for if I have a number of threads or a number of processors and I had a bunch of work to do, what are some basic techniques to make sure that the workload is distributed evenly onto all the workers without incurring too much overhead in that distribution? Today is going to be adding in the extra thinking of it's not just about good workload balance. It often is about reducing communication and synchronization overhead. So today is going to be a lot more about communication. So I'm going to talk about reducing cost of communication between processors. Again, techniques that you as a software developer might use. And then at the end, if there's time, I'd like to go into some general program optimization tips that are not necessarily relevant to your assignments or anything like that, but now that you have so much background, it might be a good idea to talk about that kind of stuff. So far in this course, and in all of the assignments basically that you'll do in this course, we've assumed that all of the processors are connected to some shared memory system, or in other words, there was one address space and all threads could read and write to variables in that address space. And I've given you some hints about, even though that's conceptually simple, the actual underlying implementation of the ability for all processors to read and write to all variables is actually pretty complex. For example, if you have like your multi-core CPU, that address space where the data, is all of the data might be stored out in DRAM, but lots of copies of that data are stored in your various caches. And the first thing Kunle is going to talk about next week is what starts happening, or at the end of next week, is what starts happening if this core makes a copy of some data, and this core makes a copy of the same address, and they both write. Now all of a sudden, we've got a real challenge because I have different parties in the system writing to the same address. There might be different values of these copies, and that can become a big mess really quickly. So we'll tell you a little bit about how modern systems keep everything coherent. If I take kind of a standard Intel CPU these days, it has a couple of cores, there's a GPU on the same thing, there's a network on this chip that connects all those cores and gets them all out to the same memory system. And these networks can be quite complex. So for example, in Intel architectures, all of the various processors are connected together and to memory actually by a ring. So there's we just think about it as load and store to the value x, but load and store to value x from a processor here, this is like the 4 cores, is actually sending a request out on this ring that ultimately gets routed out to memory. And in different parts on this ring, like if it's a cache hit, it might actually go to one of the pieces of the cache and get the data out of the cache. It can be quite a complicated thing. Actually, one thing that's kind of interesting is, did you notice that all of the different cores are kind of connected to, or if you think about this as being a core plus its piece of the L3, notice how everything is connected to the ring twice? Do you have any idea why they do that?
Is that to reduce latency? The ring?
Well, first of all, yeah, it is. And first of all, it makes things simple if you're always sending messages always in clockwise order. So things like deadlock and stuff are not much of a problem. And if you want to reduce latency, if you get hit, if you're touching, if you have 2 contact points, exactly. So if you're going to go to your left neighbor, your right neighbor, and you can only send right, you can actually get there a little bit faster. Mm-hmm. Here's another processor. It's actually a processor that Kunle was a big part of the initial design of this technology. This was done by Sun at the time where Sun existed. Then it got bought by Oracle later, but the UltraSparks. And this was one of the first mainstream multi-threaded chips. So it had, in this case, 8 cores. And each of those cores had a bunch of threads. But all of those cores were connected out to the main memories via what's a crossbar switch, the CCX's crossbar. And a crossbar means that every core is actually like physically wired to every other one. It's like n squared wires for n cores. And what's kind of interesting is if you look at the chip diagram, the actual area, the footprint of a processor core is about the same as the footprint of the network. So like these networks that get high bandwidth connection between all the processors are extremely expensive and extremely complex. And even in a simple, oh, by the way, if I go to this, it actually means that depending on what core you're at, an L3 cache can actually be a different cost based on what the address is and where it actually is and which of these slices of the L3 cache. So this is like a sharded cache where different addresses go in different places. Another example of it is if you just go out and buy a motherboard that has 2 sockets in it for 2 physical CPUs. Let's say there's two different 4-core CPUs. There's an on-chip network, that ring connecting the cores, the one I showed you, and then there are traces out over the dual socket board, and a load or a store from like core 1 to address X in that diagram might be a lot faster or a good bit faster than a load and store from, let's say, core 8 to address X, regardless of the caching behavior or things like that. So in a modern system, as we get bigger and bigger, and this is incredibly true in these big, like a modern GPU and things like that, it's not just, if you think about like how close something is, it's not just it's either in memory or it's in cache. There's actually a lot more nuance to that we don't necessarily think about when we were programming because our minds would explode. But if you actually really wanted to optimize things, you would be aware of that placement. Mm-hmm. So, even though we like to just basically think in terms of like a computer as a big pile of cores connected to a shared memory, those loads and stores on how the different threads communicate, those can have very, very different costs. And if you're elite, you're actually asking, where is this address in this machine? And you might be doing different things based on those costs. Now, one way to think about communication and make it a little bit easier to reason about is to think about other designs where moving data is more explicit. So I want to talk about a different model of computing for a second, which is called message passing, which is something all of you are used to if you've written any distributed programs in a web setting. It's not like if you're on the internet, you just say, I want the data at this memory address, and all computers on the internet have access to a unified address space. When we communicate on, in a distributed system, we do it via sending messages. Maybe it's an HTTP GET or a POST or something like that, or a response. But the name of the game is I have 2 different computers or 2 different threads, and each thread, keyword now, works in its own address space. So address X in thread 1's address space is not the same address as address X in thread 2's address space. They are different address spaces. And the only way to exchange information, like every thread can load and store the variables in its own address space, but the only way to exchange information across these threads is to explicitly send a message. So in this case, rather than an HTTP request, I said, look, let's just abstractly say thread 1 is going to send the contents of its address X to thread 2 and tag the message with an ID so that the receiver on the other side knows what it's getting. Okay? And correspondingly, thread 2 is going to post a receive, which says, I want to receive the message with this ID from thread 1, and when we get the data, we're going to put that data and store it to as the contents of the address Y in my own address space. Okay? So these messages say, how to identify data in my address space, who is it going to go to, and is there like an abstract ID that the other side can know to listen to and stuff like that. So in a message passing setting, like the real world way of thinking about it is, if a shared memory is like a bulletin board where anybody can post a message without asking and anybody can read that message without passing, message passing is a little bit more like sending snail mail. Like you put up, you wrap up your data in an envelope, you address it to a particular location, and then someone is responsible for getting it to that location. Question? Yeah.
How similar is this messaging through a network of wires similar to like the internet, for example, where you're sending packets of data with your address, a source and destination?
Yeah, and any message passing system is basically going to have some mechanism of addressing. Like this is where this needs to go. And the differences between is it done at the scale of the internet, is it done at the scale of inside a single computer with threads, or is it maybe done at the scale of a small cluster of computers or at large scale with like a big rack or something like that? There might be different mechanisms for how we identify the recipient. There might be different mechanisms for how the data moves, right? Is it TCP/IP? Is it UDP? Like there are many different implementations of how to get the message to the location, but conceptually the difference is in a shared address space system, we all talk about the same addresses and we all have direct access to read and write. In a message passing system, we all operate in our own address spaces and we send messages, meaning I say, hey, here's some data, go make a copy of it and put it in your address space. And I think this will become more explicit if we go back to this example that we talked about last time, which again, to remind everybody is the workload was for every red cell, update the value of the red cell given read access to the surrounding neighbors. And if we haven't converged, basically do it again, but this time with the black cells. Okay? And I'd like you to think about implementing this program on, let's say, not a 2-core machine, but let's think about it as a cluster with 2 different computers that can only exchange messages like internet traffic or something like that. Let's say over Ethernet. So here's my new kind of like simple computer. I have a processor with its own memory DRAM, which implements its own address space. And I have some network, whether it be the internet, whether it be Ethernet, whether it be carrier pigeon. I have some way to get information from one memory to the other. Okay. And yeah, this is just to reiterate, like I only have these 2 operations, send and receive. Okay. So here's what I'm going to do is, first of all, now let's imagine that I have to divide all the data, I have to partition the grid across these processors. And before, it was like I had one big array, right? Like when we did this assignment 1, there was one big array, and then the code of the program said, hey, thread 0 or thread 1, you should touch these addresses, and thread 2, you should touch these addresses. So now things are a little bit different. We don't have a shared address space, right? So now every thread or every machine in this cluster, and all of a sudden I jump to 4 machines just to make it a little bit easier, has its own copy of part of the array. There are 4 different allocations now in these 4 different address spaces that hold the data that each worker is responsible for. So you see that difference conceptually? Before we had a shared allocation, we all just kind of we touched our own part of it. Now we have 4 different address spaces. There is no way for thread 3 in this diagram to directly say load a value here. In the same way that if you have a computer in your dorm and I have a computer in my office, I cannot issue a load store from my computer that stores data to your office, to your computer. Okay? Now, to compute, let's say if I wanted to compute the value of this element here, what information do I need? Well, I need my left neighbor, I need my right neighbor, and I need the neighbor below me, which is fine because thread 3 has all this information. But I also need information that currently is stored in an address space that I cannot access. Okay. All right. So what almost all of these systems in a message passing do is they say, well, I need to be able to access this data, but I can't because it's not in my address space. So I'm going to make a copy of it and keep a copy of it here in my address space. So what I'm actually doing now is on each of the nodes, I'm actually over-allocating. I'm allocating an extra row and an extra row above and below my section. And I'm going to need to ask my neighbors to send me via a message the values that I should store in this row. And if you look at my code on the right, the side of the diagram, this is the logic that every thread is executing. And notice that it allocates a buffer that is 2 rows larger than the data that it is responsible for. Okay? So some terminology would be like, for example, in thread 2, there's an extra over allocation that corresponds to holding a copy of this data. So this extra over allocation where you're storing data that thread doesn't own or is not responsible for updating, you'll often hear that's like ghost rows or ghost cells, ghost values. That's a common thing you'll see in scientific computing. Okay. Now let's take a look at a full implementation of one iteration of the solver application written in a message passing kind of way, not in a loads and stores kind of way. So here it is. It's a little bit, the font size is a little small, but take a look at it and see, give it some talk. Now this is code that's being executed by every thread. It's like an SPMD kind of way, right? So what every thread does is going to come from its thread ID. So that's TID is the thread ID here. And I'll go ahead and give you a minute or so. It's sort of commented in some sense, but talk it over and make sure that you all kind of understand the flow here. So I'll let you discuss. Yeah, let's discuss. I want to make sure everybody understands this. This is worth discussing. So what is this thing doing? So there's a phase of sending and receiving data. There's a phase of doing the work you're supposed to do. There's a phase of sending the updated data to everybody else, and then there's a phase of determining if we're done and whether or not we have to repeat again. Okay? So discuss. Okay, so let's get back together. I think most people have converged the conversation. So let's start talking just through, make sure everybody understands this. And there was a question about good, and I purposely kind of didn't clarify this because I was going to get into it a little bit more later. Like, how does a send and receive work? So if I'm a thread and I call receive, that will return when some other thread has send, right? So in some sense, it's like when that call returns, the data is now with me in my address space. So technically, if I call receive and nobody sends me anything, I'll just wait there for forever. Right. Okay, so let's just take a look at this code and look at and pick out some of the details. So one of the more interesting things is just the allocation at the top. So I have this variable local A, which is just this thread's local copy of some portion of this whole conceptual grid. And local A has rows per thread plus 2 allocation. So it's my fraction of the array plus 1 row on top and 1 row on bottom. And notice that these calls to send and receive, the if statements are just, if I'm the first thread, there's nothing to my left, so I don't need to. But notice that they're storing data into the first row, or the first row of local A, or in fact the last row of local A. So the data that I send and receive kind of goes right into my local array at the top or the bottom. And I did that so that when I iterate with actual memory accesses, I don't have to differentiate between what's like the ghost row and what's not the ghost row. At that point, I just put all the data where it's supposed to be, so my code is simple. Okay. Now that's good? Yes?
Well, it seems to me that the first and the last tradition should also have like one ghost row each.
They should. They all allocate the same. In this case, the last one it doesn't have a ghost row underneath it, right? And so that data is allocated, but nothing is ever written there. Okay. So it's just just to keep the code simple. I didn't want to put a conditional around the allocation.
I was going to ask what happens in that middle network kind of top and bottom rows, it is going to be reaching into that unallocated.
Did I mess this up? So I'm going from rows per thread.
It starts at I1, I-1 would be 0, the 0th row.
Yeah, so I'm starting on the first row and on the next row, and then, yeah, I think I just didn't guard that properly. Sorry about that. Yeah, because if you look at this example, now I'm only showing the ghost rows for thread 3, but as you pointed out, there'd be a ghost row here and here. There'd be a ghost row here. And to be honest, if you recall our code from before, it would just iterate from I equals 1 to I equal to like the last row that we compute values for was this one. That was the definition of the problem, right? So I was a little sloppy, but I hope you get the point. Right, okay. Okay, and then kind of an interesting thing is, remember last time we had in the shared address space, we had the lock and we had the barriers. But there's no locks and there's no barriers here. So how is this message patches code? Like, can you describe to me, and I know there's a comment here on the slide, but let's just talk it over in our own words. How do we determine whether or not we should keep going? Yeah.
Is it all the receive? Do we wait for all the receives in that for loop?
Which one right here?
That one, yeah.
Okay, so look at this. So it says if thread ID is not thread 0, so every thread but thread 0 sends its local diff. If you're thread 0, you wait to receive that local diff from all other threads. You do a calculation to compute whether or not we are done. So thread 0 determines this calculation. And then actually sends the Boolean value done equals true to every other thread, which is then received right here by every other thread. Okay. Now, of course, like we could have done it, I could have just computed the total value and sent the total value back, and everybody independently could have computed if we were done. But that's just how I did it in this code. So why is there no lock in this code?
It's like by receiving your landing, so you're not going to touch it.
Correct. And even more fundamentally, why would we never see a lock in any message passing code?
There's no shared.
There's nothing shared, so there's nothing to maintain mutual exclusion on. So the only way to synchronize is via these messages. Right? So we've essentially we've created a situation where everybody sends a partial sum to one player or to one thread here. One thread does all the math and then gives the result back to everybody else. Why do we not see any barriers here? Yeah, essentially the barrier is inherent in this communication pattern that I did. Exactly. And since everybody has their own copy of the done variable, because there's no shared address space, there's no worry about like someone starting in the future and overwriting something that somebody else receives. Okay? So the communication is really, really explicit in these sends and receives. Okay? And so just like a summary is, notice that all of the array computation was relative now. So if I go back here, just keep in mind that all threads are iterating over the same indices now. They're iterating over the same indices in their own local piece of the array. Whereas before in the shared address space, I did some math to make sure that everybody was iterating over different indices. So it's another example. So array indexing is relative. Communication is performed via sends and receives. In this case, we decided to send many elements at a time, and then, for efficiency, do one send instead of a bunch of little ones. And synchronization is not done through locks and barriers. Synchronization is manifest in how we construct the messages. Now, there was something that you all assumed. There was a question from the back that got to this. Like, wait a minute, let's just make sure we understand the order of things that happen in what's called a blocking send and receive. So the sends and receives that I just showed you that we all kind of assumed would be if the sender calls send foo, data from the variable foo in my local address space, in the sender's address space, will be copied kind of into the network. The network will transmit the message. And assuming that the receiver has called receive on some of its own local variable bar, the receiver will get the message, copy whatever is in the message into the local variable. And when the receiver is done copying that data and has that data, it might send an acknowledgement back to the sender, and the send call returns once we are guaranteed that the receiver has the data. That's a blocking send. And similarly, a blocking receive, this receive returns when the receiver has the data in the appropriate variable in its address space. Okay? Yes?
What if the data never arrives? So when the sender sends the data, but it never arrives?
If there's a network failure, for example, right? If there's a network failure in this simplistic definition of blocking send and receive, the receiver never returns, just for now. Yeah.
The sender wouldn't get an acknowledgement.
And the sender never returns. So you're kind of thinking about it like I'm in a network distributed programming environment, failures happen, I need to be robust to it. Now take this, and let's just say you bought a 16-core computer and one message from one core couldn't get to the L3 cache. You throw it out. Right? Or all of the reliability of the protocol, let's say if we're talking about a network on a chip, all of the failure retransmission is going to be handled at the hardware level. And so a message send from one core to, like, if your processor stores to memory and you get a error, sorry, you throw the machine out, right? So that's kind of how I want you to think about it right now. Or you should think about it as there's something underneath this API, maybe some system software or something that will do all of the retries and just keep retrying until that thing happens. Okay. Obviously, you could think of alternative APIs that, like, the send could fail. Like, let's say the hardware returns some error code. The API could say, well, it didn't get sent, and it will return an error code or something like that. But trust me, if you're like writing code like this, you're not checking your error codes on whether or not like memory doesn't work and stuff like that. Okay, so you all discussed, and you all correctly told me how that code on the previous slide worked. But nobody told me that there was a fatal bug in the code. Let's go back to the code. I'd like you to take another look at it. I'd like you to tell me what happens if I run this code with blocking sends and receives. So everybody, I want everybody to take 15, 20 seconds to think about it. My hint is that it will be as bad as this comment just a second ago if memory does not work. All right. So it feels like I see some eyes lighting up. Anybody want to tell me what's wrong? Yes.
All the threads are blocking on send first.
So imagine that all of you in this room are sort of or everybody, like imagine like every processor is like a row in this room. And so the first thing all of you do is you look, I guess in this case, you look backwards, or you send backwards. Right? That's what you're doing. You're sending backwards, and your send will complete when the person behind you acknowledges or makes a matching receive. But what did the person behind you do? They're looking back. They're sending backwards too, so they're never going to get around to that receive. How can we fix this? While still only using blocking sends and stuff like that. Yeah. Okay. Yeah. No asynchronous operation. You can only use blocking sends.
Leave. You can just say that one row looks back, the other one is forward, first, and the other one back, forward, and so forth.
Yeah, so a simple solution would just be pair everybody up by their row parity. So first row sends back, the next row, first thing is they receive forward. And then you can set, that would be like one way of doing it. I guess if you look carefully, some people sometimes say, well, won't the first row, because they don't actually send anything, won't it work? And it actually doesn't even work because like the first row, if it doesn't send back, it sends forward. So everybody's going to do a send before they post their first receive. So this will deadlock under any conditions. There's a form of deadlock, right? Like you are not making any progress at all because you're waiting on someone else who also can't make any progress at all. So good. So moving forward, like, one possible implementation would be to pair folks up by parity. And so you say, okay, I'm going to have a partner, and for each partner, someone's going to send first and someone's going to receive first, and so on and so on. Okay. Question? No? Okay.
It just feels really terrible.
It feels like a very small mistake could cause your program to walk. Absolutely. So we could also go in a different direction. We could also go in a direction where communication is asynchronous. So last time, when we were talking about Silk, I talked about an asynchronous function call, a function call that can carry on potentially concurrently with the caller. And a message, you could think about it as, it could also be an asynchronous function call. So here's an asynchronous send and receive. So now when a thread calls send, it's more of like, I want this message to be sent at some point in the future. So the sender calls send, but send returns immediately. Right? You don't know at this point, you meaning the thread, you don't know that the data is gone or has been sent yet. So typically the API will give you back a handle. Like it just says, hey, if you ever need to know if this is done, here's the ID that you can use to check. So I'm calling that H1 here. So at some point in the future, so this thread can just keep running. At some point in the future, the message library gets around to copying the data to the network and pushing it over. And at some point, the receiver will get around to actually doing the receive. And once we know that the data has been received, we can probe the system. We can say are you done? Which I'm writing here is check the send status. Check the send of that message, and if that returns true, it's now I'm guaranteed that the data is gone, and I can delete, I could do something like delete foo or modify foo. Notice that if I do anything to foo in between this point and this confirmation, I have no guarantee that the message passing library has picked up the data and sent it over the wire. It'd be like me putting a package out on my porch, telling UPS to come take it, and then me changing the contents of the package before UPS shows up. The modified message is what's going to get sent, right? Or if I remove the package from the porch, UPS is going to say, you told me to come get it, and there's nothing here. Okay. On the flip side, on the receive, this is an asynchronous receive. So if I say, I want you to receive a message that I'm expecting, that returns immediately with a handle. And then the receiver at some point later can say, hey, is it here yet? Is it here yet? Is it here yet? And if so, I know I can touch the data in bar at this point. If I read bar at this point, it's unclear what data I will get. So that's the asynchronous version of these things. And so the asynchronous version can make it easier to implement some things like what I just talked about, because you're not so worried necessarily about deadlock. That's a really good point, is what will happen in, let's say this send and receive were a library, which is what it normally would be. If you were the library implementer inside of send and receive, you definitely would be putting various what's called memory fences or other things in there so the compiler would not reorder around those instructions. So I'll talk a little bit about that in a lecture later, which is about implementing synchronization. Yeah?
How do acknowledgements work in the system?
Well, the acknowledgements would be an underlying detail of the communication transport mechanism. So they don't appear on this slide on purpose. From the consumer, from the thread's perspective, what I have available to me is I initiate a send, I essentially get a tracking number, which is the handle, and I can check via that tracking number later if the send is complete, yes or no, or maybe if it failed. Now, how under the hood the network layer implements reliable transport, that's a completely different story and outside the scope of this class. Right? Mm-hmm. Yes.
When you have two consecutive sends, how does this setup handle?
So in this slide, if I said send foo, and again, foo is the variable that I'm sending in my local address space. If I set send foo again here, and these were asynchronous, it's pretty undefined what will happen because there's no guarantee of what order those two messages would be sent. They're actually both sending the contents of the same local variable. So are you saying, what if I had send foo and then another send fizz or something like that? I mean, I'm just sending two messages. So there's no guarantee that they will be, unless the library gives you states guarantees, there's no fundamental reason that they would arrive at the receiver in the same order. Yeah. Unless like there's some configuration on the message passing API which says if you set this flag, we guarantee you it will be in the same order. Yeah.
How do you make sure, so would you just busy wait here?
Yeah, so one way would be to busy wait. Another way, some libraries might be designed in that you register a callback or other things. Like in asynchronous JavaScript, it's more like essentially posting that AJAX request is like you're putting yourself in a queue and you get invoked when it's done. Mm-hmm.
Just about the ordering of the receives if they're sent in sequence. I think previously there was a message ID also being taken.
Yeah, like the way you would do it is, I'm just being simple here. I would send foo ID whatever, and then the receive, you could either receive most of these APIs. You just it's very specific now to the threading to the message passing. You might say I want to explicitly receive the message with this ID, or you just post receive and say I'm just receiving. And then once you have checked the receive, you say, oh, the message is here, and here's the ID of what it was. And then your program might be, oh, if it's ID 43, I do this. If it's ID 42, I do that. Yeah. So every message you should think of as having an ID, and sending or waiting or receiving can be wait for a message, any message, wait for a message from this sender, wait for a message with this ID. Those are all parameters and details of your message passing thing. Okay. Now, even though I set this up as imagine these are different computers communicating, I want you to just keep in mind that there's many different types of communication. So there's no difference conceptually if we're talking about communication between a core and its memory, or two different cores on the same chip, or two different computers in different dorm rooms. Abstractly, we can send messages between anything, right? And communication can be between, movement of data can happen between the processor and its registers, or its local L1, or its L3, or DRAM on my own computer, or DRAM on somebody else's computer, or DRAM, off in Google. So communication, I want you to think of as just being abstract, right? And once you start thinking about this, these diagrams that I showed you a few lectures earlier, where I said, imagine a processor issues a load instruction, and there's some memory latency, and then the data has to actually start moving back to me. So now hopefully you get a little bit of a sense of where all this memory latency comes from, right? It's an L1 cache lookup, an L2 cache lookup. Maybe you actually have a TLB miss because of, in operating systems or something like that. Maybe a request, a message has to get sent to memory saying, I want the data at this address. And at some point, the memory starts sending you the data back. And if you have a bandwidth of B bits per second, you start getting B bits per second back in that blue region. Okay, and so that's why when I drew this thing, I drew an example like this, where this was, remember, it was a program that it did two instructions and then a memory transaction. So it's math, read, math, read, math, read. And the main idea of this diagram is, well, if we just look very carefully, first of all, even though the reads don't come back for a while, as long as the processor has some ability to hide the latency, like multi-threading or something like that, we don't really care so much about the latency. We actually care the most about the length of the blue bar. So if you look carefully at this diagram, just double convince yourself that memory is always busy. And the processor is not always busy. And I drew these yellow bars to show you that memory was always busy, and the pink bars are times when the processor is not executing instructions because it's waiting for the next piece of data to come back from memory. So you can think about this blue bar as being it's a cache line. It's 64 bytes or something like that, if every one of these reads is a unique cache line.
Question. So is this message passing an alternative to what we talked about last time with the worker queues, or how does it work together?
Message passing is just a way to exchange data between threads. An alternative on how to pass communicate data between threads is everybody reads and writes to a shared address space, right? And so the reason why I brought up message passing, other than to make everybody familiar with the idea of message passing, is it's kind of helpful to think about communication in the context of message passing, because like you literally see it in the program. Here is where the communication is. Whereas what we talked about in assignment 1, or like this was an example that I used for the bandwidth bound problem in assignment 1, where's the communication? Well, the communication is the load and store, but that load and store is actually about sending a request out to memory and getting the data back. So the communication in a shared address space program is kind of implicit in the implementation of memory. So, I'm just like but I could implement shared work queues using message passing on a bunch of machines on a cluster that had no shared address space, right? I could do that dynamic work stealing with different queues very easily, except now, stealing work is about sending another computer a message and getting work back, as opposed to directly accessing their data structure. Okay? Yeah.
So if you're writing a program on a practical system where it's not a cluster but just one processor, is there ever a reason to use message passing as opposed to threading?
There definitely can be. There definitely can be, because in some sense, message passing forces you to think about all the communication. So a lot of folks do actually write with a message passing model on a multi-core shared memory system, just because locks are hard. And like if messages were like throw something in a message queue and let the other side pick it up, that can actually be an easier way to reason about concurrency. Like, for example, in most multi-processing systems, you might send a message to another process as opposed to memory map the address space into both processes and stuff like that. So message passing is a highly structured form of communication, which forces you to work hard to get it right. But once you get it right, communication's really explicit. You kind of know where any stalls might be. It might be easier to debug and performance tune. Shared memory is just a different mechanism that doesn't force you to have any discipline at all. So it might be easier to get your first program running. Maybe you just throw a big global lock around everything or something like that. But as you start to performance tune it, now you don't get maybe as much structure or as help. And there's different reasons why you might want to use different things. Yeah.
Sorry, one more question about performance. It seems like when we're doing message passing, there's this extra write that's happening where you have to first write to the network.
There's a copy, yeah.
Yeah.
Yeah, there's a copy in and out.
Is there any way to get around that, or is that?
There are plenty of ways to get around that, right? Let's go back here. In a modern high-performance network, even a modern data center where you got a bunch of machines, and let's say you're running a key value store that needs to be distributed over a bunch of machines, there's a lot of interest in reducing the latency and the cost of sending messages. So it could be very easy that this send foo, this foo is a variable, this is a pointer. And the only thing that happens is that pointer is sent to your NIC, and your NIC reads that data out of memory directly itself and pushes data out over the wire. So there are very high performance networking implementations that don't necessarily mean that data is copied unnecessarily. But even in that implementation, until the data has been, at some point it has to get copied because it's got to get copied into the network. Until that copy happens, any modification to foo by the calling thread could in fact change the bits prior to that copy, which means that even though you thought you were sending the contents of foo when I called the thing, you actually send the contents of foo later. And that's going to be a bug. So asynchronous, all of a sudden, if it's synchronous, you never think about concurrency between the caller and the message transmission. Asynchronous, like it was suggested that it might be an easier way to do things. It can also be a harder way to do things because now you've introduced more concurrency in your program and you potentially have more problems. Okay. All right, so let's see here. I talked about this, a few lectures ago, but I wanted to put another slide. This is something I'd like you to take offline. And, when you look at this diagram here, I want you to be able to go, yeah, that program is bandwidth bound. It is basically communication bound between memory and the processor. And I'd like you to be able to answer all of these questions. Like, if you increased memory latency, which means if you increase the distance from here to here, would any of the utilization or efficiency change? And your answer should be no, as long as you can hide that latency, right? If you increase the bandwidth of the system, what would happen? The blue bar should shrink. And if the blue bar shrinks, that means I'm stalled less in the pink regions. If I increase the number of math operations per blue memory request, utilization goes up. Those are all things that I want you to be able to think through. And at the end of the day, it all comes out, if we're not worried about latency, if we have the ability to hide latency, whether it be multi-threading, prefetching data, or whatever, the name of the game is going to come down to something called arithmetic intensity, which is the number of math operations you're going to do per unit data that you read. Okay? Some people like to call it communication to computation ratio, which is 1 over this. I like arithmetic intensity because A, it kind of sounds cooler, and B, higher is better, which is intuitive for me. Yeah. Okay. So let's talk a little bit about, a few more ideas about communication. Okay. So you will find that it's helpful to break apart communication in 2 ways. One is communication that just has to happen because of the nature of the algorithm. And another one is communication that happens because of the way machines actually work. So the first one is called inherent communication. The second one is artifactual, and that comes from the fact that I have some real details of how a computer works, and there are artifacts of that. So let me just give you an example here. Okay, so in this grid solver application, I cannot do the application. I can't get the right answer unless I move this data to this thread. That is inherent to the computation. So that's communication that just has to happen. Somehow, I have to pay that cost. Okay? And we talked a little bit last time about, well, how much communication is there? Let's take a look at this. So if I partition my work across my processors, sorry for interleaving P1 and T1, and processors and threads to me are the same in this lecture. How much communication do we do for every element that we process? So what is that ratio of elements processed to amount of communication that happens? So let's think about one thread. If the total amount of data is n squared, and divide this up amongst p processors, how much work does every processor do? N squared over p, right? N squared over p, right? And how much communication does every processor do? 2p, right? So if we have n squared over p, I'm going to drop my constants, and I have 2n communication. Oh, did I say 2p? Oh, sorry, yeah, 2n, right? It's the width of the thing. Well, then my arithmetic intensity is n over p, right? Sorry, n over p. Now, if I went with this interleaved assignment, and we think about the message passing program, what is the amount of computation I do? Still n squared over p. And how much data do I move? To n squared. Or another way to think about it is for every row that I compute, how much data do I have to move? 2 rows of data, right? So now my arithmetic intensity has gone from n over p, and let's just assume that n is probably a good bit bigger than p, to 1/2. So if I go back to that diagram where the speed of my utilization is going to be a function of can I not be bandwidth or communication bound, here I'm doing n operations for every p elements communicated. There I'm doing 1 operation for every 2 elements communicated, and I'm much more likely to be bandwidth bound with the scheme on the right than I am on the scheme on the left. Okay, can anybody think of how to maybe do better? So left is way better than right, for sure. Can you do better than the left? Yep.
If you block it,
So the arithmetic intensity, very good, is basically it's the ratio of the area of a region to its perimeter, in this case. And the way to create a shape that has the highest ratio of area to perimeter is what? Is a square, right? So let's look at this. Let's divide up the work this way instead. I had to create a few more processors here just to make the diagram a little bit more obvious. So now let's just say I have 9 cores. And so again, I have n squared elements, p processors, What is the work per processor? Stays n squared over p. That hasn't changed. What's the communication? Well, every one of these borders is square root of n over square root of p, right? So the elements communicated is basically 4 times n over square root of p. Did you follow that? Okay, because I divided something of width n. I have p processors total, so there are square root p processors along one row. Okay, and so now my arithmetic intensity, before, remember, it was n over p. Now it is n over root p, which is a larger value and potentially very important if my p is large on a large core count machine. Right? So this trick of redistributing the work in this tiled format as opposed to the chunks of rows means that I have higher arithmetic intensity. I'm doing more operations per byte sent, and I can stay running at full utilization with lower memory bandwidth. Or if I'm under a machine with a lot of cores, I have higher utilization for longer.
Isn't the shape of the minimum ratio of area to perimeter, isn't that a circle?
Well, I mean, you could, but go for it, yeah.
Would be complexity to add that circle versus like the
I mean, it's going to be up to you. If you are bandwidth bound, if you're communication bound, anything you do to increase arithmetic intensity will translate into enhanced performance. Now, you want to cut this up into circles. What are you going to do with the regions inside the? I'm not exactly sure. You're probably going to waste so much math at that point to figure out what you're doing that it may not be faster. But this is a pretty substantial improvement. In other words, think about it this way. Imagine you're running on a 64 core machine or something like that, or let's just say a 16 core machine. Root p versus p, that's a 4x difference. Like, you can maintain peak utilization with 4 times less bandwidth using this scheme. That can be a really big deal. Okay, so that was an example of an optimization to reduce inherent communication, because that was data that had to move. Often we're fighting a bunch of stuff that is artifactual communication, which kind of comes from the fact that we never move one data in a piece of data in a computer. We always move a cache line, or the minimum packet size might be a kilobyte or something like that. So there's always details of how a machine works where you're like, oh, that communication shouldn't be so bad, and then you're like, oh gosh, that was really bad. So let me give you a common example, which is caches. Why we teach caches in this class. So think about the caching behavior of the grid solver. Okay, and so imagine that I have a cache that the cache line size is 4 elements. So each of those blue things is 4 dots wide, so it's 4 elements. And imagine I have a cache that is 6 lines, or 24 total grid elements. So imagine that when I'm computing that red dot there, as a result of computing that red dot, I read the 4 cardinal neighbors, and hopefully you agree with me that these would be the cache lines that would be loaded. So after producing that red dot, those would be the cache lines. I move over horizontally 1 element. Will there be any cache misses? No, actually. They're all cache hits. And now imagine just, we proceed in the horizontal direction. When we get to the end of the row, I've computed all of these elements, and that is the state of my cache. Remember, my cache can hold 6 lines. Okay. Now I want you to think about what happens when I get back to here. I want to process the red dot. My cache has the blue region in it, but not too long ago I had all the data that I needed except for the row underneath the red dot sitting there in cache. And now it's not there, so I'm going to miss on everything again. That's kind of artifactual communication, right? Like, theoretically, I loaded that data, and if I had some magical cache, I'm not communicating it back to the processor again. But if you actually looked at this program, you would say, no, I'm taking all these cache misses every single time I touch data, right? So if you look carefully, this program, for every 4 elements of output, I load 3 new cache lines. That's one way to think about it. That's probably easier to see here. If I go, once I get into steady state, So notice here, the first element, 3 cache lines. The second element, no new cache lines. The third element actually is going to load 3 more cache lines. But in steady state across the thing, I'm going to do 4 red dots for every 3 cache lines that I load. Okay? So that's my arithmetic intensity. 4 elements of output per 3 cache lines. That's a ratio of work to bandwidth. Okay, and there's a lot of examples of artifactual communication, like cache lines or finite-sized caches or network traffic that has to be transmitted on boundaries of size 16 and stuff like that. So my blocking example, that tiling, that was an example of changing the assignment of work to processors to reduce inherent communication. So when I divided the world up into tiles, I said, okay, if I do a different workload balance, you're going to communicate less. Because inherently you will communicate less. Now let me give you a technique for reducing the artifactual communication. Or in fact, maybe you can come up with a technique on, instead of running across the array like this, is there a way I can change the program to increase its arithmetic intensity? Yes, sir?
What's the inherent communication here?
Inherent communication is, given the scheme, like given the assignment scheme, how much data actually has to move between the processors to actually get the job done. In this example, actually, I removed parallelism. So assume that this is all going on inside of one thread, right? So now I'm saying that even inside of one thread, there was before communication across the processors or across the workers. This is communication within a worker between the processor and its own memory. So can I do better? Yeah.
Maybe if you go across the top and then just move down one and then go right to left, like zigzag pattern.
So my goal here is when I come back to the left, I want to come back quick enough before the data has fallen out of cache. Right? That's like what's going on. So if I change the, let me jump forward again. If I change the order in which I iterate over this array, I compute the same answer. I'm just going to iterate in a different order. This is not about parallelism again. This is just about communication. Now, whenever I get back to here, some of the data that I've already accessed is still valid and in my cache, and I only have to load this one new line below me. And if you carry this pattern out, before it was 4 pieces of output for every 3 lines loaded, this new pattern is 6 elements of output for every 2 lines loaded. So I've again increased my arithmetic intensity pretty substantially. This is called cache blocking. This is probably the most important technique that you will ever do in any kind of code that involves tensors and matrices and stuff like that. So any modern matrix multiplication, any modern tensor operation, the reason why cuDNN is so fast is because of choosing really good orderings to move over the data. Yeah.
Would it be faster if you iterated in reverse order across the rows, like going?
If I iterate in reverse order across the rows, you mean all the way across and then all the way back? Yeah, that would also be a reasonable scheme here. Kind of. Actually, it would not be a reasonable scheme here. It's a reasonable scheme if you look at this diagram, but imagine n being really wide. If n is really wide, sure, you get a little bit of reuse at the ends, but you're back to this failure mode in the middle. So yes, on this diagram, you'd look at it and go, yeah, most of the reuse on the ends is about everything, but now imagine n is 1,000. Yes.
For myth, like our cache is like in the order of megabytes large.
But not your L1, it's 16K or 32K or something like that. Yeah, I think it's 32K, yeah. Yep. And a matrix can be quite big, like a 2K by 2K matrix is blowing out your L3. Yep. Mm-hmm. Yep.
Like, is there a way for us to figure out, from the code, without us having to think about, oh, hey, this is like kind of exactly what's going on. This is the exact bandwidth with the cache stuff. Is that a way for like us to figure it out? Just like some code like profile is that like allows you to
Well, profile will tell you what your arithmetic intensity is. Like, tools can say you are bandwidth bound. They'll tell you that, but they're not going to tell you how to fix it. Mm-hmm. So here's another example that pops up in all of your lives very often. So here is a program that might look, I wrote it in C, but it looks a lot like code you might run in NumPy or something like that, right? So I have a bunch of library functions for multiplying arrays or adding arrays. This is very much like Saxby from assignment 1. But usually if you have that library, you might do a more complex calculation on arrays by basically performing some expression, which I wrote here in C code. Right? So each one of those library functions has the arithmetic intensity of basically our thing from the slide before, right? Like it loads 2 values, does 1 math op, writes 1 value. Okay. And so any program that is created by composing these library functions, if all of the library functions have arithmetic intensity 1/3, your program is going to have arithmetic intensity 1/3, right? So this is a really convenient way to write code. It's like you just write it like this, and hopefully every one of those are these big vector operations, and it's in pretty bad shape. Now here's an example where I took the program and I rewrote it. I rewrote it by, instead of iterating over all elements and doing the add, and then iterating over all elements and doing the mul, I'm iterating over all elements, but for every element, I'm doing the entire expression and then writing the result. So why is this better?
Iterating over 4 arrays instead of 6.
So I'm iterating over 4 arrays instead of 6, but in particular, that's a way to say it, I'm reading the value from A, B, C, D. I'm computing all of the intermediates, which probably get stored in a register or in cache. And then I get all the way done with all of that stuff and then dump the result out. So as a result, as pointed out, I'm iterating over far fewer. I'm doing far fewer math operations. So in this case, 1 math operation for every 3 loads and stores. In this, I do 1, 2, 3, 4, 5 math loads and stores, and I do 1, 2, 3 math operations. So my arithmetic intensity has gone from 1/3 to 3/5. And given that we know that this is bandwidth bound, my speed up is going to be how much I improve arithmetic intensity. So this is a common optimization that a lot of the deep learning compilers are now starting to do for you. You want to kind of write your code in terms of adds and muls and in terms of these vector tensor operations. But you sure as heck don't want it to actually run under the hood like that. So in a high-level language like TensorFlow or PyTorch JIT, that's what these things are doing. They're taking your tensor program, which looks like these operations on vectors, but they want to execute it in a manner that looks like this. And then, it's fine. We're not going to get into like co-locating threads to share data across threads today. Okay. All right, so let's see. So how are we doing? 11:38. All right. Any other questions? I have this section on contention, and I actually want to. I'll give it like 2 minutes, but I'll let you kind of read it offline. I don't think it's the completely on brand for the lecture. One thing I just wanted to point out is that what I'm trying to stress is, at the end of the day, everything you do is going to be ratio of bytes communicated to amount of work you do. That's the point I want to instill. This section is just pointing out that sometimes when you do that communication or when you do that work matters. So let me just give you one example. Imagine you all come into office hours, and you come into my office hours, and the steps would be, you take 5 minutes to walk over to my office, you wait in line if necessary, and you get your question answered, let's say in 5 minutes. Pretty useful office hours. So the latency here is what? It's at least 10 minutes, and plus your waiting time in line. Okay. So the first student that shows up in my office hours immediately starts talking to me. They take 5 minutes to walk over. We start working on their question. immediately. So 5 minutes to walk over, that's the yellow bar. 5 minutes to deal with their question, they're done in 10 minutes. The next student that arrives at office hours, maybe they come also like right on time, but right after the start of office hours. They take 5 minutes to walk, but then they got to wait for 5 minutes behind somebody else in line, and then they get their question answered. So it's like basically if people arrive at my office hours all at the same time, there's going to be contention for me, and the later you come, the longer you're going to wait. Right? It's kind of an inefficient thing to have happen. Like the bottom of the slide, student 5 is kind of screwed. So this is a contention for a shared resource. And so this is a little bit of a different concept than everything I've been talking about with bandwidth. It's like the amount of work and the amount of travel time of all of these requests are the same. It just so happens that one's behind a queue. Whereas instead, if like you make an appointment with me and I give you an appointment, well, you can be guaranteed that you can be in and out in 10 minutes, right? So that's actually why I kind of like appointment-driven office hours, because it's a lot more efficient for the students. Okay, so the time cost the student is 10 minutes. And so when we were talking last time about contention, we talked about it like the shared mydiff variable, the shared queues. Last class I was talking about how we often like to replicate things to avoid contention. And in memory communication, the contention is for memory, right? So it could be the case where if all processors asked for data from memory at the same time, some of this beautiful like pipeline diagrams and stuff that I'm drawing maybe don't quite actually work out in practice. So that's why I just wanted to put this wrinkle in there and say, in practice, usually in many systems, there's not a lot of contention. So we think in terms of averages, like bytes read per operations. But if all of those bytes read happen to happen at the same time, memory could appear to be a lot slower than it really is and stuff like that. So, people do, like in the work queue setting, we talked about different work queues. In the memory request scheduling, you'll actually see sometimes it's good to actually randomize things to avoid contentions. Like everybody leave their house and get on the highway at a random time. And then the highway is it's more likely to get peak bandwidth and stuff out of it. So just a little aside on when stuff happens really matters. So what do we talk about? We talked about a number of different techniques. So we talked about reassigning work to workers to reduce inherent communication. We talked about reordering the order that any one worker does things in order to reduce artifactual communication, in particular cache locality. And so we gave you just a couple of examples of stuff like that. Cool. Okay. So let me just finish up on just a few tricks and some stuff. So reminders going forward as you get into assignment in these assignments. One is sometimes the simplest dumb static solution with no optimizations is faster than a complex solution. Always try the simplest thing first in this class. Okay? If it works, great, move on. Go work on some other class. Okay? And then the question is, when you're not happy with your performance, one question that I always ask myself is there an opportunity to do better? So you ask this question about like, how do I get measurements to know if I should just keep trying? So in assignment 1, you made a lot of measurements that told you whether or not workload was well balanced. And that was really helpful because like if it wasn't balanced, you could work a little harder. But what about measurements about am I bandwidth bound or not? So, one technique would be to go grab a tool like vTune or any of a performance profiler, and it might just tell you. But there's a lot of other tools that are kind of interesting, like let's say that I know that I am computing at this many instructions per second, or in the math, like this many megaflops. Well, if I just knew the total megaflops of my program, my computer, I could ask the question, what fraction of peak megaflops am I actually getting? And that might give me a sense of whether I should keep trying or go on, right? So there's these graphs that are pretty useful graphs. This is actually something worth really knowing. That is a way to plot where you are on the curve. So let me explain this graph to you. This is so the x-axis of the graph are different arithmetic intensities. It's labeled operational intensity because some people call arithmetic intensity operational intensity. It's the same thing. And notice the units are flops per byte. So that's math operations per byte read from memory. Okay? And so these different points on the x-axis are different programs. If I move along the x-axis, I'm talking about a program that does 1 op for every 4 bytes from memory. Or on the far left, a program that does 16 ops for every byte from memory. So this is going to be not very arithmetically intense. This is extremely arithmetically intense over here. And so imagine that, I guess empirically, you took programs that you manufactured to have those arithmetic intensities, and you ran them on a computer. And when you run them on the computer, you're going to get a performance in terms of operations per second, so gigaflops. Okay. If your program or if your computer can do, let's say, 16 gigaflops, has a 1 gigahertz clock and has 16 cores, and your program is compute bound, you should expect to run at what? If you're doing a good job and your program runs at 16 gigaflops, you're like, this is as good as I can do, right? So this is a plot of all of those different programs, what they actually achieve. And let's see if you can explain the shape of this graph. It's called a roofline graph because it looks like a roof, right? So let's start over here. And I just want you to look at this line and this blue line because this is one computer. The other line is a different computer, so it has a different roofline plot. But let's just look at this blue line. This blue line says that for all programs of arithmetic intensity 1 or higher, when you run them on this computer, you get the same performance. Does that make sense? And if it does make sense to you, why?
It must be memory bound.
Okay, so it must be memory bound. Why is that?
Because you have greater intensity, so if you work memory bound, you should expect to be doing.
Okay, let's take a look at that. So these are programs that access memory less and less often, right? Higher arithmetic intensity, less frequent memory access. So as I do less and less memory access, my performance is unchanged. So wait a minute, right? Yeah, so anyone want to help? Yeah. Uh-huh.
I guess that's like the maximum clock speed of the processor itself. Like it can't go any faster.
So this is basically saying for these programs, I'm doing so many operations per unit byte read, my performance is limited by what my arithmetic units can crank out. And I'm maxing them out all the way until this point. And then at this point, my performance starts going down. Why is that? Yeah.
At that point, it's memory bound.
At that point, you can't get data to the processor fast enough in order to run these ops. And so though, as you begin to lower arithmetic intensity, it takes you more and more time to get the data to the processor in order to carry out the ops, right? Because before it was like 1 byte per op, and now I got to get 2 bytes per op. So it takes me half the time. If you look at this as a log plot, I used to get done at 16 gigaflops. I double the amount of bandwidth per op, which means I double my runtime if I'm bandwidth bound, which means I half my performance. Exactly. So if you look carefully at this, the slope of this curve should be the bandwidth. But okay. So now imagine you have a program, and somehow you kind of look at your code and you kind of know what your arithmetic intensity is. Like you kind of look at the main loop, you're like, okay, it seems to be, you did this in program 1. And so you're like, okay, I'm, let's say, at arithmetic intensity 4. And then you run it, and you compute that you're like right here on the graph. What does that mean?
You're not going as fast as you can.
That means that this should not be memory bound, and I'm a good fraction off of peak. Something is wrong, right? Maybe I have workload balance. Maybe I have contention. Maybe I have something. So that's like this graph gives you this like, where do I stand kind of point. This green curve is just another processor. The other processor, even though this is called X2 and this is X4, these are actually like marketing names. This is a processor with 4 times more total compute. And so notice that with 4 times more total compute, the peak performance is about 4 times higher. Notice, what do you notice about the memory bound to compute bound trade-off?
You have more operational intensity before you beat them.
It's the same memory system, but with 4 times more compute, which means you need approximately 4 times more arithmetic intensity to stay bandwidth bound, or to stay, compute bound. Okay? So if you buy a computer, you pack it full of parallel capability, that's only going to run at peak performance if you have applications that have the math to use it. And the way you make your application go this way on the chart is you do the things I talked about in class. You fuse loops, you block loops, you reorder things to reduce communication. So almost everything you do is trying to drive your program this way so that your program performance rides up on this curve until you hit the flat line. That's basically the name of the game of everything. Okay, we should stop, but I'll answer these 2 questions and get out of here.
Is there ever any situation where you want to go left? Like maybe you're like really far out in that operational intensity, and maybe is there ever?
If you're way out here, and you never want to go. Well, okay, so this curve says if you're out here, you're running at peak performance. What is your wall clock time? Your wall clock time is how much work you're doing times the rate. So if you could change your algorithm and it moves you in this direction, but keeps you on the roofline, and that algorithmic change means you do less work, then you're in good shape, right? Because I'm running at the same peak performance, and maybe I have something that's algorithmically more efficient and does less work. So this is a plot about efficiency and throughput, right? So if you make a change and it reduces your arithmetic intensity, but like makes you do 10 times fewer things, if you stay at high throughput, you're doing 10 times less work at the same throughput. That's good, right? But if you change your algorithm and you do 2 times less work, like you make a computer graphics algorithm improvement, and that algorithm change brings your arithmetic intensity from like here to here, it could be a wash, because you might be doing 2 times less work, but twice as less efficiently, and so maybe it doesn't matter. Right, so that's maybe the reason why you would move down the curve if you felt like there was an overall benefit.